If you end up servicing something that you've never seen before, you're going to find parts that you've never used. And in this case, you're going to have to pull a data sheet to figure out how they work, and you're going to have to read through it. So I really encourage students to start looking at these data sheets and figure out how they work. This is the LM2596 datasheet, and I'm going to point out what I think are the most important sections. So the first thing I noticed here is in section number 5, they talk about the tolerance here, 4% tolerance on the output voltage, and a 15% tolerance on the oscillator frequency. So if you're scoping this, you should look for those kind of things. It's within spec if it's within 4% of the output voltage. The part comes in 2 packages. There's the TO220 and the TO263. One has a metal tab that you can screw to something with a hole, and the other one is a surface mount version that needs to be soldered right onto the circuit board. There's 5 pins shown here, and the function of each pins is listed down here. The absolute maximum ratings gives you things like the highest voltage that you can put on the input, so you shouldn't exceed 45 volts, and it gives you some lead temperatures here. This is important information for soldering. Then they state some electrical characteristics, and they like to do this for each version. So here's the 3.3 volt and the 5 volt version. The 3.3 volt version typically puts out 3.3 volts, but the minimum that you should ever see is 3.166, and the most you should ever see is 3.432. This is with the junction, the internal junction on the semiconductor at 25 degrees C or room temperature, and then they also give you a range of output. So this is with VIN between 40 and 4.75 and the output load between 3 amps and 0.2 amps. Under those operating conditions, you should see 3.3 plus or minus a certain output voltage. And then they're giving you that same type of rating for the 5 volt version. You should get 5 volts plus or minus 0.2 volts. This line here is the efficiency, and the 3.3 one is 73%, and the 5 volt one is running about 80%, and that's with VIN at 12 volts and a load of 3 amps. That's a significant improvement over our linear regulators. Then there's some electrical characteristics, and this is for all versions. And there's some good stuff here. The feedback bias current is typically 10 nanoamps. And what that means is you don't really need to have a lot of current going back through the feedback pin in order to regulate properly. Oscillator frequency, saturation voltage. This is the voltage across the transistor when it's on, and it's at most 1.5 volts. So if you want to put 5 volts out of a switching regulator, you need to add 1.5 volts to the input of that. So you need to apply at least 6.5 volts on the input in order to get 5 volts out. So this 1.5 volts, that is the dropout voltage. That is the voltage that you will drop across the switching regulator. Section 8.2 shows you a more detailed functional block diagram. Here's the switching transistor that pulses the output, and that goes to the LC circuit. All of these guys have a 1.235 volt reference. The fixed voltage versions have a voltage divider built in that turns them into 3.35 and 12 volt versions. There's a 150 kilohertz oscillator, and that using a latch turns the output on. So when this gets latched high, the output comes on, and then it senses the feedback line to turn the latch off. Then there's usually a few application circuits. This one here is an under voltage lockout. So here we have a 12 volt Zener, and that's going to be in series with that 0.7 volt diode. So this particular circuit, VN must be greater than 12.7 volts in order to turn this transistor on. And when you turn that transistor on and short out those 2 points, then you have pulled on low, and then you will get your power up. So this stops the regulator from turning on until there's enough input voltage. Section 9 now starts getting into how to choose the components. For example, 9.11 talks about the input capacitor, and we need that to be a low ESR. That's equivalent series resistance, and that is essentially a low impedance to high frequency. So we need this capacitor to work fairly well at high frequency. So for that, you need a low ESR aluminum electrolytic or a tantalum capacitor. Ceramic capacitors are better for this, but they don't come in large enough sizes to work here. So it's going to be an aluminum electrolytic or tantalum. The output capacitor also needs to be a low ESR electrolytic or solid tantalum capacitor, and it should be designed for switching regulator applications. Because these things are working at a reasonably high frequency, you want to make sure that any capacitors you use will filter out any oscillations. The catch diode, so that's this diode here that is before the LC network on the step-down regulator. Now that should be a Schottky diode because of their very fast switching speeds and low forward voltage drop. A Schottky diode is probably one of the best choices here. You can also use an ultra-fast recovery or a high-efficiency rectifier, but pretty much everything in these switching regulators is a Schottky diode. Rectifiers such as the 1N5400 series are much too slow and should not be used. So a fast diode is one that when you close the switch and you apply a voltage on the input side, the current starts flowing almost instantly. That's what they mean by a fast diode, is it turns on really fast and it also reverses really fast. If you take it from reverse bias, forward bias, it conducts current almost instantly. So here's a table of inductor manufacturers and some part numbers. There's Schott, and here's some through hole and some surface mount inductors from them. Renco, Pulse Engineering. These are all inductor manufacturers, and these are all pretty common part numbers. So if you're looking for a 47 microhenry with about an amp of current capability, you would want to pick one of these four. If you liked Coilcraft, then you go to the Coilcraft site and you go for that one. Section 9.2.1.2 kind of runs you through the design procedure here. They suggest you go to the TI website and download the WebBench tools. And then the first thing you want to do is pick your inductor, and then you want to pick your capacitor. Here's a selection table. It has some common values that you could choose from, like a 47 microhenry inductor and a 270 microfarad capacitor. Here's some instructions on how to select your catch diode. And then there's also a table of some available parts that may work. Then there's the input capacitor, how to choose the input capacitor. Here's some notes on how to do circuit board layout. They're telling you which traces need to be fattened up when you do your layout, and they must be kept short and use a ground plane construction. So you want to run these traces, let's see, between the input capacitor and the chip. You want those to be fat traces so that they can pass high frequency better. And then later on in section 11, they're giving you some suggestions on how to do layout. They're saying that you should lay it out using a ground plane construction, and what that means is that you should use polygons instead of small, thin traces. You should use surfaces. High frequency stuff likes to travel on the surface, so let's give it lots of surface. This reduces high frequency impedance. So start spending a little bit more time with the data sheets instead of the textbook. My joke in the past has been that I won't be around there to read it to you, so you need to start reading them. And I realized here in the latest version of Edge that you don't even have to do that because there's a read loud button. So you just push that button.
The LM2596 series of regulators are monolithic integrated circuits.